Hi, so welcome everyone. My name's Chris. Been coming up for a while, so you might recognize me. If not, welcome. It's your first time. Happy to have you. I'm here to talk about strings in C++, specifically Unicode strings, and all sorts of stuff that you might need to know, but also might not. Let's get started. So Unicode and C++ are both very big topics, but I want to focus on the intersection of the two. I will touch a little bit on some specifics of Unicode to give you some context if you're not familiar. But for the most part, if you want to learn more about Unicode, I've got a number of great talks I can recommend you. There's a lot of really good online resources. Unicode itself is nothing new. It's been around for decades. There's a lot of really great learning resources. So if you're dealing with anything outside of the most basic text operations, and frankly, any programming language, I think it's definitely worth your time to spend a few hours learning about Unicode, since it is the standard for text encoding in the modern programming world.
Good.
Yes.
Can you take questions?
Yes, if you raise your hand.
One of the 9 standard identifiers with, I know one of them's in IO stream, at least one.
It is. So there are 9 standard library identifiers with capital letters. That is outside the scope of this talk, but we will get back to that. So try not to look it up if you don't have to, but rack your brain. There's at least 9, and if there's a 10th or more, then I want to know, because it's one of my favorite pieces of trivia. But it is sadly not related to this talk. So just like C++, Unicode is a PDF. And that's to say it's an ISO standard. It's a big document. It's not, it's just a lot of words, to put it very simply, but it does a couple main things. So one of the first things it does that's very useful is that it assigns integer values to a unit of text. And a unit of text, kind of a vague term. We'll talk more about terminology in a second. Suffice to say, there's a lot of different units of text. They're more than just the letters that we think of in the Latin alphabet, or the letters, maybe the Cyrillic or the Greek alphabet. Those are included. Those are units of text. There's a lot of units of text that gets rather complicated, to put it mildly. The other big thing Unicode does is that it finds 3 different encodings. So if you have a sequence of these units of text, there's 3 main ways you can encode that into an actual stream of bytes, called UTF 8, 16, and 32. The numbers correspond to the whether it's 8, 16, or 32-bit. So let's talk a little more about what all these words mean. If you want to talk about Unicode, you need to be kind of picky with your language, because Unicode itself is rather picky with terminology. So character is not really a term that Unicode uses. It is in the glossary if you go look it up, but they define it in kind of a loose way. So for talking amongst us, it's useful to say it's like the smallest human readable unit of text. So any one of the letters on the screen, the thumbs up emoji, those are all kind of a unit of text, to put it casually. But that term doesn't have a strict meaning. So while I might happen to use it more in this talk, bear in mind that it's not a term of art in Unicode. It's kind of loose, but the following 2 terms do have strict meanings. A code point is one of those integer values that I was talking about. Unicode defines a mapping from integer values to units of text. Each unit of text is called a code point. That's the term of art that Unicode uses. So the thumbs up emoji is code point 1F44D, or in decimal, it's 128.077. They're just numbers. These are not encoded. They're just kind of numbers in the abstract sense. Emoji are some of the highest. I believe there's up to maybe 1 million code points, of which maybe somewhere in the low hundreds of thousands actually exist. So there's a lot. There's definitely room to grow with more. So if you want to invent a new language and it really takes off, then maybe you can wind up with your own code points. A code unit is actually something that's dealing with the encoded form of the text. So I mentioned how there's 3 main encoding formats: UTF 8, 16, and 32. The number refers to the bit width of the code unit. So in C++, that's going to correspond to the 5 different character types, which we'll talk about more in a moment. So just think, for UTF 8, the code unit is an 8-bit unsigned integer. For UTF 16, 32, it's 16 and 32-bit. So when you're looking at actual encoded text, it's going to be a sequence of those code units, which there's a number of different sizes based on the encoding you choose. So let's look at a few examples of what this looks like. The algorithm for encoding is outside the scope of this talk, so I won't be getting into that. But I want to show this to demonstrate how the different encodings might require different numbers of code units. So if you look at UTF-8, there's 4 blocks for up to 4 code units. But some code units don't need all that space. And that's why it's called variable sized. So for example, the Latin capital letter A, which in ASCII is 41, is also just 41 in UTF-8. A really fun fact about UTF-8 is that it is a superset of ASCII. So if you have ASCII text, you also have UTF-8 text. So you can just read any ASCII text as UTF-8. And that was one of the core design principles behind UTF-8 that makes it so valuable in today's programming world. But some characters are outside of ASCII. So E with an accent is a slightly bigger code unit. Its value is E9. The U plus syntax is a really good way to look up code units. That's how Unicode itself refers to code units when you're looking at documentation, or there's a number of really great websites that consolidate information on Unicode code points. So if you want to look up a code point, the U plus prefix is a really useful way to kind of disambiguate your search query. So E with an accent happens to be 2 bytes, but in UTF-16 it's still 1 byte. This Japanese character in the 3rd row happens to be 3 bytes. It has a larger code point, so it needs 1 more byte to encode it, but still just 1 byte in UTF-16. And then emoji uses all 4 bytes. At most you're ever going to have is 4 bytes for a code point when you're encoding UTF-8. And in this case, you need 2 bytes in UTF-16 to encode that. But you'll notice that in UTF-32, it's always just going to be 1 code unit. There are up to, I believe, 2 to the 21 possible code units. So those fit squarely into UTF-32. So that is kind of a naive encoding. It's just 1 to 1.
You said 1 byte to encode it, but I think you mean 2 bytes minimum UTF-16 for like the A code point is 2 bytes.
The terminology is
4 bytes.
That's correct. It's
One
one code
code
unit.
unit. One code
Thank
unit,
you.
but yeah.
Yeah, every code unit in UTF-16 is 16 bits. It's 2 bytes, and you can't slice those apart. It's just going to be either 1 or 2 16-bit code units. Thank you. Yeah, you have to be really picky with your words because Unicode itself is pretty precise about what these words mean. So that's most of what you need to know about Unicode itself. Now let's actually talk about the programming language itself. So there's 5 character types in C++, 4 if you're using 17 or prior. First of all, char, we know that one. We're familiar with it. It's been around forever. It's always just a byte. The syntax for making it, it's just you put single quotes around it before you make your character literal. It usually means ASCII text, but already we're getting into some messy territory here. It could mean UTF-8. If you're dealing with something like a standard string, you could be dealing with UTF-8 text. If you have an API that takes a standard string as a function parameter, you can't stop users from encoding UTF-8 in there. And for that matter, you can't stop them from encoding anything else in there. Any other 1 byte code unit encoding, of which there are many, could be stored in a standard string. So while char typically means ASCII, or at least historically it's meant that in cases, it could mean UTF-8, which is, I would say, increasingly likely. And it could mean even something else. Wide characters are messy in their own different way. They're 2 bytes on Windows and they're 4 bytes everywhere else. Just fun historical reasons for that. I believe that might have predated the standardization of the language. I don't recall the history on that, but with this has the capital L prefix to denote a wide character. On Windows, this means UTF-16. On all other platforms, it means UTF-32. Historically, this meant UCS2 on Windows, which is an older encoding, which is a subset of UTF-16. But as far as I can tell, that's mostly an artifact of history now. And if you're working with wide strings on Windows, you should be able to safely assume that it is UTF-16 everywhere. So with the UTF-8 code unit, it's messy again. Prior to C++20, you could use this U8 prefix and you would get a character, just a char. After C++20, they added a new strong type called char8t. It is a character type, just like the other 4 here. It is not interchangeable with char. You cannot implicitly convert between the two. You can static cast if you want, but they are different. I'll talk more on that in a second. In 11, they added char16t and char32t. These are pretty straightforward. They have a lowercase and a capital U prefix respectively, and they mean UTF 16 and 32. The standard does guarantee that if you're using these, you are getting UTF 16 and 32. So they've been around for a while, and they do mean what you think they mean. So luckily, the story with those are fairly straightforward. So if you're dealing with UTF 8 strings, auto is definitely your friend. This U8 prefix has been around for a while. If you'd like to use it, totally go for it. But just bear in mind that if you take code written in 17 and you compile it in 20 mode, that is something that we assume to be valid, but it is a hard API break in the language. I think it's probably worthwhile. It is annoying, but I do think the state of things in 20 is better. So it's frustrating, but yeah, it is one of those rare hard API breaks in the language. So the sideness of char and wchar are platform dependent. So you might have known that about char. It's signed on Windows, it's unsigned on ARM Unix, it's signed on x86 Unix. I've looked into the history behind this, and I think you can find some reason, but if you're trying to look for a bigger picture kind of way to remember where it's signed and where it's unsigned, you just kind of have to memorize the table. It's a bit annoying. You can explicitly request that chars are signed or unsigned. There's signed char and unsigned char. So you can explicitly say, I want signed or unsigned. If you omit that, you get whatever the platform tells you. And I didn't realize until I wrote this slide that wchar is the same way. It also has different signs on different platforms, on top of the fact that it has a different size on different platforms. So when you see a wchar in portable C++ code, it could be in an unsigned 16-bit int, an unsigned 32-bit int, or a signed 32-bit int. So it's a little messy. And what's even worse is that you can't signed or unsigned wchar. You just get what you get. If you want it to be unsigned, you just have to deal with it. The good news here is that you typically don't have to really care about this. I think it's worth knowing, but ideally you should be writing code that is agnostic to the exact size or signedness of these. So I guess maybe keep this in mind if you were serializing, unserializing things, if you're moving these in and out of the network, that could be an issue. But outside of that, you should be able to just kind of move on as if this slide never existed.
So I think I'm right in thinking that char is weird, right? Because independent of char, signed char and unsigned char are different types again. Like it's not the case that char and signed char are the same type even when char is signed. Is the same thing true of wchar-t? We don't know.
I mean, the standard treats character types as different from their kind of equivalent integer types. That's what you're saying?
I'm saying you can write a function overload, 3 different functions that take char, signed char, and unsigned char. And they're all different types. And
that's my
it's
understanding.
weird. Okay. Is the same true of wchar-t and the other?
Well, there is no signed and unsigned wchar-t.
Because they're not numbers historically.
It just is
Okay.
like if you try
So
to say
you
like
can't
if you type
apply-
signed wchar-t, that is not valid code. That is not
Okay.
something you can express on the type system. So if you are working with, say, Windows and you actually want a signed wchar-t, you just have to use int16t. Assuming your platform has it, which it doesn't necessarily have it.
At least 16t.
Right. int16 t.
Yeah.
Okay. So it's been like 15 minutes and I haven't talked about strings yet. But now we're talking about strings.
In the burn.
I like to break down strings into these 3 parts. There's a prefix, the contents of the string itself, and the suffix. The prefix is your encoding. You saw in a previous slide, all the different character types are disambiguated by their suffix. So there's capital L, UA, lowercase u, uppercase u, and the absence of a prefix, which is just sharp. So that is your encoding. So if you want to say I want a UTF-8 string, that's what the U8 prefix works for, capital U, UTF-32, and so on. The contents are, generally speaking, because there's always exceptions, encoding agnostic. So what you put inside the string, that is just the code points you want in your string, kind of in an abstract sense. You're not thinking about the byte representation on disk. You're just thinking about what code points or kind of what characters, to use that term loosely, do you want in the string. And it can be whatever you want, including emoji, and all sorts of other fun stuff that we'll talk more about in a moment. And then the suffix is the container. So the absence of a suffix is a character array, which we know implicitly decays to a pointer and all that fun stuff. There is an S and an SV suffix for string and string view. But that's just the way that the container that it's stored on disk. Or sorry, that's the type in the type system, I should say. So when you combine all these, you have 5 different prefixes and you have 3 suffixes, you get 15 different string types, string literal types. So already there's a lot going on. For the character arrays are just, there's not like a named type for them per se. I guess you could say like char, brackets. But for basic string and basic string view, they all have named versions. So if you look closely, the top row is straightforward, string and string view, we're familiar with that. There's also W string view for wide strings. UTF 16 and 32, the story there is pretty clean. There's U16 string, U16 string view, and so on for UTF 32. And then that pesky UTF-8 prefix is kind of getting us here. So again, in pre-20, use the U8 prefix on a string, you're getting a standard string. It is still encoded as UTF-8. It's just using a code unit of char. And then 20 and beyond, the U8 prefix was changed to mean a U8 string. So that's a basic string specialized on char AT, or same for basic string view. And there's the corresponding U8 string and U8 string view types you can use in your code to refer to that. So I think this graph, this grid is a really good way to picture it. I didn't fully realize until I was digging into this that there are, for every prefix and for every suffix, there are types in the type system for all of these. So whatever you could want, it should be there. But actually, there's 30 different types of string literals because for every one of those 15, there's a wide string version. So you have 5 character types in 3 containers with 2 variants, either kind of conventional or the raw string literal version. So there's actually 30 different types of string literals. And then once I realized this, I was like, okay, now I guess I'm gonna get a talk on this. So this is kind of what led me to go down this route when I realized there's 30 different versions of string literals. Raw string literals are cool because they let you include characters that are typically escape sequences. So the quotes themselves, you can include in the string. If you want to include like \n, that won't be escaped into a new line. It'll just give you \n inside your string. So in this case, I'm showing an example of like a JSON literal. I also work with some code where we use these for SQL queries. SQL includes, I believe, a number of characters that are going to be typically escaped. You can just put backslashes before all of these characters, but then it becomes really difficult to read. So raw string literals work right here. They work with all the prefix types, all the suffixes. Do note that the parentheses inside those outermost quotes are not part of the string. So in the comment below that, that's actually the contents of each one of those strings. The parens, in addition to the capital R prefix, are kind of part of the syntax and like the machinery for making raw strings work. You can also just like include new lines in here. So you can just go like after my name, quote, comma, you can just press enter, and that new line will become part of the string. So I've also used these for like GLSL shader code. If you're familiar with graphics programming, you can put entire shader programs as like big raw string literals in your code. And it looks just like source code because you have new lines inside your string.
Question which you might be coming to. How are the literal suffixes implemented? Like if you wanted to write a UDL, how do you deal with the different encodings? What happens in your UDL?
That's a good point. I'm only familiar with UDLs as long double and character pointers as the parameters you're given.
Right. SV and S are implemented somewhere in the standard library, right?
It's a really good point. How would you make your own user-defined literal that's based off of, say, like a U8 string literal?
Wouldn't it take a UN?
But I'm only aware of user-defined literal.
UDLs have pretty fixed signatures, don't they?
I'm assuming that there's one for the WHRT or.
Yeah, I don't know.
Yeah, it might just be a bit of an oversight.
Yeah.
You know,
I don't know, I'll see the reference at the end, maybe. It could be.
And there,
so,
there's 30. We just covered that.
yeah. So byte string literals are not as useful because they have a different code unit and a different encoding. They're not very portable, especially if you're dealing with anything that goes through the network. I think these are only useful if you're dealing with Windows APIs. If you are, then those are expecting 5 character pointers pretty often. So not much to say here other than if you're trying to figure out what type of string you want to use, you can largely ignore these unless you're dealing directly with a Win32 API that needs them. Okay, so now let's actually put some Unicode characters in the strings. I think this is where you start to get stuff that's actually really useful and expressive. So as per the standard, this should just work. You should just be able to put emoji in your string, and with the right prefix, you get what you want. I think there was a defect report that actually rigidly defined that these prefixes do correspond to UTF 8, 16, and 32. It's like that is strictly guaranteed, but MSVC breaks that. If you don't include this /UTF 8 flag with MSVC, you will get garbled text. This was confusing at first when I was learning about this, and it was another one of those reasons I wanted to give this talk, is that you might think you can just put emoji directly in your string, and it will work on everything except MSVC out of the box. But you do need this flag to make MSVC standards compliant with this corner of the language.
Where do you have to put that?
It's a compiler flag. So
Okay.
somewhere where you're adding compiler flags in your build system, just make sure you add this to MSVC and MSVC only.
Okay.
There's no reason, I think, to avoid using UTF-8 encoded source files. It's really space efficient because for the most part, you're just getting all these ASCII source code files. Source code characters are just being encoded as 1 byte. And again, with this flag on MSVC, everything should just work fine. That includes comments as well. If you want to put emoji or non-ASCII characters in your comments, I don't really see any downside. So I don't think you should feel compelled to use ASCII source files.
Is there some weird, for example, let's assume I have millions of lines of code and I didn't use UTF-8. Is there some code breakage if I start using it? Do I have to be careful, or can I just ignore it?
You should just be able to, so your editor will probably do this automatically. Let's say you have a 1,000,000 source file and it's entirely ASCII and you add 1 single emoji to a comment. Chances are, if you're using an editor that's remotely Unicode is decades old at this point, it should encode that emoji as the 4 byte sequence required. And that should just be it. Your file will, when you add the emoji, it'll become 4 bytes longer than it was before. Everything else is the same. And your tool should understand that just fine. So that's why I think by default, if you use something like the file tool on Unix OS, it'll show that your files are ASCII or something like that. If you don't happen to use any like non-ASCII characters, if you add just one of them, it'll be UTF-8. Doesn't really matter. Everything, all your tools should handle that gracefully.
But there's some corner cases though, because if you do like strlen of something, you're going to get that byte counts as 4, not
Yeah,
as
strlen
1.
tells you the
So
number
you
of code
suddenly
units.
like,
Yeah, the number of code
something
points.
might break still, right? I need
yeah,
to-
because you get the number of code units. Not
Yeah, I talked more about the limitations later, but you're right. Yeah, that is something we'll cover
So
more
it
today.
depends on,
Yeah,
so something might break, yes.
yes, that's what I'm afraid of, adding it that command line.
Yeah, if your code assumes ASCII and you start feeding it Unicode strings, it will. The compiler will handle your source files just fine, but if you actually put emoji in the strings themselves and you have other code, the strings that assumes ASCII everywhere, then yeah, you might have issues. That kind of gets back to what I was saying earlier, where if you work with standard string, you don't know the encoding. You have to assume the encoding. Strings themselves can't carry that information along with them. You have to carry that information out of bounds somehow. You have to, out of band, sorry is the term. So you can just say that our code base uses UTF-8 everywhere with standard string, that would work. You could say it only means ASCII, or it could be, yeah, like I said, any number of the other kind of less popular encodings, but that's like a contract you have to uphold with yourself.
There's a comment online. the answer to how strings literal prefixes handled with UDLs appears to be write the UDL function with overloading. There is a link to compiler explorer.
Okay, I'll have to play with that. So for whatever reason, you don't want to put non-ASCII characters. If I say Unicode characters, that's a casual way of saying non-ASCII characters. ASCII characters are Unicode characters, so it's a bit loose way to refer to it. But if you want to put Unicode characters, if you don't want to put them in your source files, there is actually multiple ways to avoid that, and this is one of them. I think it's one of the best ways. There's a feature called universal character names. So within your string, you can use the /U or /u prefix as an escape sequence, and then provide either 8 or 4 characters corresponding to the 4-byte or the 2-byte representation of the code unit. So again, the hand up emoji is 1F44B. That's the code unit value in hex. And you have to include the 3 leading zeros because it is expecting all 8 characters for the 4 bytes. And then lowercase u is just a shorter version of the same syntax where you only have to write 4 characters, but it's too short to encode emoji because emoji requires 5 hex characters or more. Don't be confused. This is another case, just like the word static in the language, where capital U and lowercase u are hijacked to mean something different. Uppercase U doesn't mean UTF-32 inside the string, as a prefix does. Inside the string, it just means the 8-character version of the universal character name. And lowercase u doesn't mean UTF-16. It just means the 2-byte or the 4-character version of the code point. It just is what it is. You might kind of start drawing connections and be like, oh, that's like a UTF-32 code point. It's not like that. It's just a reuse of the syntax. So I said how the contents of the string are typically encoding agnostic. This is the exception. So if you say, no, I want to put this exact byte for this code unit in my string, you can use hex escape sequences. So the first example is a char-based string where I just say it's hex 41, 42, 43, which is all caps ABC. If you added a like lowercase u prefix to this, it might mean something different. Because you're saying, I now want these bytes interpreted as UTF-16, which I believe would coincidentally work, but it's coincidental because you're specifying the encoding here. So you better know exactly what you want. For strings with larger code units, like UTF-16 or UTF-32, you can specify 4 characters or 2 bytes, or up to the full 4-byte hex literal for your UTF-32 string. So you can see an example in that UTF-32 ABC where it's /x 1F44B. And this is also how you can have string literals with encodings that aren't natively supported by the language. So that's a Latin 1 encoding right there, where it's hex A1, A and B map from ASCII map directly into Latin 1, but then the C with the part below it, which I wish I could tell you the name of that French character, is hex E7.
Cedilla.
Okay. I can't repeat what you said because I didn't quite hear it, and I'm afraid to mispronounce it.
Cedilla.
Cedilla. Okay, I trust Ben. That's hex E7 in Latin 1, and then the exclamation point is, or rather, the E with an accent is hex E9, again in the Latin 1 encoding. So this introduces some more weird syntactic nonsense with strings, more reason why I'm up here in the first place. When the compiler sees hex A1A, it thinks that's 3 hex characters, and it sees the B and says, oh great, that's 4 hex characters, which will be a compiler error because 4 hex characters is 2 bytes, and we're using a string with no prefix, which means the code unit is a char, which is 1 byte. So it says that it thinks you're trying to use a hex literal that it's 2 bytes wide with a 1-byte code unit. That doesn't fit, it's not gonna work. So you have to add those 2 extra quotes. So you basically end the string after hex A1, and then you start it again with AB. Those just will get concatenated by language. This is just one of the things in language will do, is that you can put character array literals next to each other, smush them together, and it'll just work. And then again, after the hex E7, character D appears like it could be a hex literal, a hex character. So you have to, again, do double quotes to escape that. So it's pretty clunky. But there is a better feature, and I'll get to that in a moment. better way to write that. I'll also note that if you want to just have like a buffer of data that's not like semantically a string, this is a way that you can kind of make a literal buffer. If you don't want to do curly brace and then have comma delimited values inside like an initializer list or something to initialize a standard array, you could also use this. I've seen that used in code bases before. No one.
The chill mod, sure.
We have 2 legitimate uses of octal in the room. They're not confident. I think they're just being supportive because they care for me. So thank you. But I don't believe that you actually use octal. But it exists, and I have to talk about it for the sake of exhaustiveness. Octal is weird. It is a base 8 number system. Due to how it works.
Everyone uses the individual 0, so everyone uses octal.
Yeah. Thank you. Octal 377 is as high as you can go. Any higher and you exceed the value 255, which no longer can be stored in a byte. And it's a little worse here because you're thinking, well, let's say I'm using a UTF-32 string, capital U prefix. I've got 4 bytes for every code unit. I can use a bunch of octal characters because I can store way more than 1 byte. It doesn't compile. I don't know why that limitation exists. You can have hex escape sequences that are 4 bytes wide. You can only have octal escape sequences that are 1 byte wide. There is a new feature that fixes that. I'll have to spoil the next line. But that's one of the limitations of octal. So if you want to encode like an emoji as an octoliteral in your UTF-32 string, you can't do it. Very niche use case, but for anyone in the room who's upset about that, I'm sorry, crush your dreams, you can't do that. Unless you have 23. Someone really cared about these escape sequences. I should thank them after this talk. I should go find a paper and thank them for that. It is a good feature, I do quite like it. So there's delimited escape sequences, which is basically the same as before, but the start and the end of the sequence are delimited by braces. So for the first example, it's longer than the previous version. I'll just flash back real quick. So if you look at the first line, hex ABC, it's fairly simple. Now it's like twice as wide. So it's not very useful there. But if you skip down to that last line, the Latin 1 string, now you no longer need the extra quotes. If you use Clang format, it will add a break after each quote. So it'll really butcher the formatting of your like exotic encoding string literals. So that's like a nice little benefit of this. It also fixes the problem with octal, not being able to encode values greater than 1 byte. So now when you have open close brace, you can use octal escape sequences, which are, I suppose, as big as the underlying code unit, which is as big as 4 bytes, 32 bits. So that works just fine. There's also a new escape sequence, which is /u with the braces, which we saw before, but now there's a delimited version where you don't have to have the leading zeros like you did with the /U. You can just do /u and then with the braces, put your code point value inside of that. Gets even worse. So Unicode defines names for every code point, which again, there's like over 100,000, up to optionally 1 million in the future. That's how much space they have. All of them have names, and the names are standardly defined, which means languages like our beautiful favorite language here has a feature where you can just put the name of the Unicode literal directly in there. In this case, if you can't read the slide, it's /N, and then within braces, it's the standard name in all caps for the Unicode code point. Again, if you can't read this, this is rightwards harpoon with barb up, rightwards harpoon with barb down. And the comment is what that character actually looks like.
How are the error messages for this? Like, what if I misspell harpoon?
You know, when I wrote this slide, I was actually really, like, I had a program where I was test compiling all this stuff to make sure it worked. And I was really nervous that I would type it wrong, and I typed it correctly, so I never saw the compiler error. So I guess I'm just, what I'm saying is a skill issue, I guess. It's like 11 words.
Just type Control X8 enter. Then start typing.
That is a good point. Yeah.
Like your editor will.
Now I am curious. If someone wants to pop up Godbolt after this, I do want to see what are the compiler errors if you mistype this, or give you a hint. That'd be really.
That's what I would
I
hope
expected
was.
to see.
If it was like one character off, it's like, oh, you've been like with Harpoon down. Again, I don't really know what the use for this is. If you're artificially limited to ASCII source files, why are you using C++23? Like, that seems like a weird thing to have. Have like the cutting edge language standard, and then also we can't use UTF-8 source files, which UTF-8 is like 25 years old or something. I don't know, but it is nifty that exists. There's maybe some readability angle here. I picked a very long name for the sake of this slide being a little funny. A lot of them are shorter. It's like Latin E with accent or something. Like maybe you have a use for that, but more for like the less exotic code points.
You have a question? Does that let you have characters that are like right to left and a left to right text file, or that are like combining with other characters, other things that you don't want your editor to try to like display?
So you
Like
could
backwards
just
delete.
put those in your source files.
Okay, the backwards delete character.
I guess there are, yeah. So there are some pretty exotic code points.
Yeah.
And I guess if you, any code point that you can express in like text, you can copy and paste, should be fine.
Yeah.
But I suppose if there's code points that you can't like copy and paste conventionally, then yeah, maybe you would have to either use one of the numerous ways to specify the code point or this, spell it out. So yeah, that actually, it could be a use case.
It's not just an editor thing. I mean, you have to have the font,
Mhm.
right? The editor can deal with everything fine, but if you don't have a font with that glyph in it, it's gonna not show up right for you.
Yeah, well, in your editor, it will render as like a box with an X or something like
Yeah.
that.
It makes for a bad code review.
Yeah, it's
That's
like a
the
bad
wrong- that's
like
the wrong
developer
box.
experience thing. If you like, because the encoded file will have the bytes that you want, the compiler will get it, and then your coworkers are like, this is just like boxed with X over and over again. So yeah, that's a good point. If you're using, yeah, I tried some really wacky stuff, and at least VS Code's text rendering, at least on my Mac, handled some really wacky stuff. So I have hope, but yeah, maybe your editor doesn't support it as well. Well,
Mine will actually suggest the closest one for you if you misspell. I don't know about others yet.
that's really cool.
Yeah.
What does MSPC do?
Cry.
Yeah, it will, did you mean grinning face?
Okay, I'll have to look at that later, guys. Thank you.
Did you mean grinning?
Did you forget the subtitle of the talk? So I need to go back. It's way more than you need to know about. The whole point is that we've already blown past the practical needs of
GCC will not suggest it.
Yeah, okay. Common claim W right there. So you can put not, again, Unicode characters, non-ASCII characters in your standard strings. And with the UTF-8 flag on NSTC, this will work how you want. So if you're working with an interface that is kind of like UTF-8 everywhere, and they use standard string everywhere or standard string view, or constant character pointers for that matter, you can just do this and it'll work. I tested, like the actual bytes on disk are what you expect them to be, to the extent that you can read the bytes of an object in C++, which then will probably tell me you can't actually do, but you can do. From what I tried,
Sometimes.
it was encoded how I expected. It worked on my machine. But it does kind of introduce like a weird API design question. If you use a std_u8 string in your interface, you're unambiguously saying this is a UTF-8 string. It's nothing else. If you try to shove like Latin 1 text into a std_u8 string, that's weird. And I think it's pretty safe to say like that was just your fault. The API makes that pretty clear. The type system doesn't technically enforce that. You can still put garbage bytes that are not actually valid UTF-8 in your U8 string. But it does make it pretty clear. But beyond the fact that's a feature from 20, which kind of raises your standard requirements, it's a little weird. Standard string is what people expect. And if you start putting std_u8 string view all over your interface, people are not going to necessarily know that. I don't think a lot of people know this U8 prefix. I don't think it's that popular. I don't actually think I've seen this used in the library. So for the sake of API design, Still kind of an open question. If you want to handle Unicode strings, what type you use?
Are there invalid
Yes.
U8 sequences? There are.
Code points, the other one, code unit.
I talk a little bit about that in a minute. You're reading my mind. These are all stuff that I touch on just a little bit, but yeah, you can have invalid UTF-8. There are byte sequences that are not valid. In fact, it's pretty easy to break.
But it's designed so that it can resynchronize it at the next.
Yeah.
Yeah, if your like decoder is smart enough, you can handle it, but your decoder has to be smart enough to handle that. And then you have to have an error channel if the user input is not valid UTF-8. So yeah, there's some API concerns. The type system can't encode as much as like I think we would want it to encode. So some more oddities here. So if you want to store a single character in quotes, because the word character is kind of loosely defined, you might think, okay, character, that's one code point. I need at most 32 bits. I'll use the char 32 team. That works. Until someone picks a different emoji. Anyone want to guess how many how many code points this is? Person shrugging with a custom skin tone.
I'm gonna say it's at least
2,
9 bytes.
3,
5.
it's 5. Okay. It's 5 code points. I forget what it breaks down into. I think it's something like the base emoji plus the skin tone modifier. I think plus a gender modifier. And I think there's also 2 joiners. So I think it's something like the base emoji join skin tone join gender, I believe. I think that's how you get to 5. So already you're thinking, I'm taking one unit of text from the user. They just opened up the emoji picker on their computer and they typed this. They just hit the key once. They clicked once, but you need more than one code point to store that. So if you want to store a single unit of text, you actually need a string. You need an arbitrary amount of data. There's a slightly more cursed version. You're welcome that it's only 18 code points. I could have made that. I had a version that I tried that was over 1,800, 1,800 code points for a hello world string. And I can see it in my presenter notes. It like messes with the text above and below it. So if I put it on the slide, it would have made the lines above and below it unreadable. The term of art for this is Zalgo text, Z-A-L-G-O. Go look up a Zalgo text generator if you want to stop listening to me and have something else to play with on your computer. It's really fun. This is the really cursed stuff. When people talk about like Cthulhu taking over their computer, they're using Zalgo text to kind of make their text look corrupt. What's going on is that there's a lot of Unicode code points that are like diacritics. They add to the previous character, but they are not kind of characters in the conventional sense. And you can stack these as much as you want. So I'm pretty sure the limit is truly unbounded. You could have the user paste a single character, and it could be like a megabyte, I guess. So maybe that's another like fun bit there.
I mean, we should say there are practical uses. It's like, I had to write a Thai font renderer once, and Thai has multiple, it has up to 2 combining things above and up to 1 and 1 below. Maybe 1. Right? So there are real languages. It's not just we
Yeah,
do this
yeah,
because we can.
It's fun to joke about this, but there's of course a very legitimate reason all this stuff exists. But I bring up the more ludicrous examples to show that if you want to make your code robust to lots of user inputs that are in the form of Unicode strings or UTF-8 strings, anything like that, you do have to store an unbounded amount of memory for that. Jonathan?
Is like, how large is the set of diacritics? And can you have the same one more than once?
I suppose you can.
What would that do?
I wish you could see what I can see in my presenter. Are any diacritics repeated? Yeah, I think I see some diacritics that are repeated. Yeah. So
You could have like an accented letter with an accent, essentially.
it's something like that. Yeah, I think it's possible. So there's like more kind of realistic examples here. So you can use the UA prefix on a character literal. And you might think, okay, cool, I can put any code point I want in there and I can store the characters as UTF-8. But remember, a character literal is just one code unit. And there's a lot of characters that are more than one code unit in UTF-8. So the Euro sign here is, I believe, two bytes, 2 code units. It's 1 code point, but it's 2 code units. So that means it won't compile because you need actually 2 bytes to store that and not just 1. So similar things can be said with the lowercase u prefix for char16t character literals. An emoji is going to be 2 char16t code units. So you can't have a char16t stored emoji, but you could have it store the Euro sign. So this is another thing that's kind of unintuitive. It makes sense once you understand the machinery at play, but it might be a bit of a head scratcher at first. Yeah.
Do you declare that last example as a carry key array and it would compile?
Yeah, in that case, it would get encoded as proper UTF-8, and you would get a 2-byte character array in the type system.
You said the person emojis can be 5+ units,
I think some are even longer, yeah.
but you said there's so many spaces still available in 32-bit Unicode. So why did they choose modifiers instead of just filling up the space?
Yeah, that's a good question. I suppose it's more space efficient within the code point space itself. Is that by combining existing code points to make more emoji, you can kind of get more value out of less space? Because there is a hard limit. I believe 2 to the 21 is the highest possible code unit, which I think is something like 1.1 million.
We don't really expect to run out though, so what's the point of making it
2 to
more
the 21 is
complicated?
2 million. 2 to the 20 is 1.
It's on the order of low 7 digits. But my point is that you can't have 2 to 32 code points. Like the nature of the encoding prohibits that. So there is a hard cap. But then after that, I don't know, UTF 64 or something. I guess I understand why they wanted to do that, but also I'm kind of having a guess
It would make
as to their rationale.
it would make your font renderer have to have more, your fonts would have to have more glyphs.
Right.
Than having 2 glyphs that you overlay.
I will say there is a similar thing where
So it would take up a lot more space.
like E with an accent is 1 code point, but sometimes that is actually encoded as E plus the accent modifier code point. Sometimes it's sort of 2 code points, and that gets into something that's kind of outside the scope of this talk called like normalization forms, where you can have what appears to be 2 identical strings that are actually encoded differently. So you might do a string compare on 2 strings that appear identical to your eyes, and like in your editor, they might look identical, but they're actually different byte sequences. So there actually is something kind of like what you're talking about in Unicode.
Okay, is there something that defines if it uses just a literal accent and E or a modified E?
If you're decoding Unicode, it's your job to handle those cases.
Okay,
Yeah.
nice.
It's the responsibility of the decoder to handle all those different ways to create what appear to be visually identical strings. So the containers we use are not Unicode aware. These strings all appear to be the same, but the size reported is different. Dot size reports the number of code units. So the number of code units is going to change based on the encoding you use. It's not the number of code points, it's not the number of characters, visual units of text, it's the number of code units. Also stuff like pushback, it's actually pretty easy to make an invalid sequence of UTF-8. So if you take a U8 string and you push back something into it, that might be valid. If you push back, say, just a single ASCII character, that's valid. But if you push back certain bit patterns, certain bytes, it will be invalid UTF. The container itself, the type system doesn't stop you from doing that. It doesn't enforce the encoding. The literals themselves are very great, but once you actually have them on disk and you want to mutate them, you're on your own. You need to make sure you're doing it correctly. Likewise, there's no per code point iteration, which could be really useful. You're getting every single byte individually. So if you have a UTF-8 string and you want to parse that byte by byte, you want to parse that by code point, you just have to figure out, you have to look at each byte and you have to understand, you have to decode the string to figure out where the code point boundaries are. Likewise, there's no normalization forms, which kind of gets at a previous question. There's multiple ways to encode visually identical strings, like what appear to our eyes as being identical. There's multiple forms. Unicode defines standard ways to normalize these strings so you can compare them byte by byte, bytes by bytes. Doesn't exist. We don't have that. We also don't have ways to convert between different Unicode strings. We used to, and I suppose depending on your standard, we might still have that. But they got deprecated. I looked into this. From what I heard, it had to do with these utilities not handling errors quite well. I believe they handled errors in band, which is say they would give you a string with like replacement characters, for example, if you were decoding invalid UTF-8 and trying to encode it into UTF-16, for example. I believe it would just give you replacement characters. And I think the committee was not pleased with that, so it was deprecated. I think it got removed in 26. So I don't recommend this for production code if it's already been deprecated years ago.
What's a replacement character?
Unicode defines a specific byte sequence, which is kind of the standard way to say we don't know any better. So if you're decoding UTF-8 and you get to an invalid byte sequence, you could optionally replace that with like the default replacement character. Good point. And that's kind of a standard way to say we have to put something here, but it wasn't valid until you get to the next valid code point, and then you keep doing what you were doing.
When you have UTF-8, does it have a mechanism to tell you this character isn't done yet? You have to look to the next code point.
Yeah, it's actually a really clever encoding, and I wish I could talk about it more. But there are some really clever ways, the way that the encoding is designed, where if you start reading a string with UTF-8, you can kind of go forwards or backwards in like a systematic way to figure out where like the next code point begins. So it's a really clever encoding. It's also like not too complicated, so it's pretty learnable for anyone, even if you're not like a seasoned programming veteran. But what if there actually was a standard way to convert strings of different Unicode encodings that no one really knew about? It's not advertised as doing this, but it's called stood file system path. Unicode string converter, and it works. It works, and I hate that it works, and no one should use it. And if you use it, please tell me, because I want to see how you do it. But this is a Unicode aware string class. So you could construct it from all 30 different string literals. All of those work. You can even use like the /= operator. You can use whatever you want. It'll store it somehow. I don't know how it stores it. It doesn't matter. And then there's member functions for getting UTF-8, 16, or 32 strings out of it. So for all the different string input types, there's a corresponding Unicode string output type. And I've tried it. It works on all major platforms. I kind of hate that I found this, but I'm also kind of proud that I found it because I think it's really neat. This could be useful. I'll say it could be useful for non-critical code paths. If you have a string and you want to re-encode it without pulling in an external library, just for the sake of printing it, and the stakes are kind of low, you're not like writing it to a file, you're just kind of like, it's for a human to read, then yeah, go for it. If this is part of your critical code path to re-encode the names of users at your bank, it'll probably work, but also I don't know what the error, how this handles errors. It just returns like a UTF-8 string, for example, when you call U8 string. The error pathway, I don't know if it really exists. I suppose it'll use the replacement character if I had to guess. But this is not designed for this. But I will say it's cool it exists, and if you really need it, it's there.
Since I don't know, does file system path check for invalid path characters? And I don't know whether, for example, if I put instead of smiley face.
My understanding is that the file system path will not do anything clever unless you tell it to.
Okay.
So if you use a path that's like home / /home / .. You're just kind of bouncing back and forth between directories. There are APIs, member functions that I believe will take that and just kind of get rid of all the unnecessary junk. But I believe you have to call that. I don't think it'll do that automatically. So it's like you don't pay for that unless you want it. So I'm fairly certain that if you input a string in here, which is like a really messed up path, because it's going to think that you're giving it a real path. I don't think it'll change the string unless you tell it to. So it should be there exactly how you initially gave it to it. Even as you add more, as you like append to it, it should just like leave it unmodified and just kind of throw the underlying string. Like I said, it should work, but yeah, I don't know. It's messy. If you're dealing with C APIs, you often need to deal with a all caps file pointer. I've worked with C APIs where we need paths that include Unicode characters. That's a common use case for our users. We need to support it, but our APIs, the underlying C API that we use, provides, I believe, two interfaces, one for a file pointer and one that takes the file name by a const character pointer. So in some cases, you can provide a const character pointer to a UTF-8 string and it'll work, but it doesn't always work for all of these C APIs. So we can use the file pointer version instead. So then what we need is we need an abstraction for getting a file pointer out of an arbitrary std file system path. Std fopen works with a const character pointer. So that works on Unix OSs because file system path cstr gives you a const character pointer. That same function in Windows gives you a Y character pointer. So it doesn't work with std fopen. So you have to call this Windows specific function called _WFOpen, which does take a Y character pointer, and that works. Likewise, your mode, the mode in which you're opening the file also has to be a wide string. So you can do that conversion with the iterator-based constructor. I think that's a convenient way. And this gives you a nice convenient way to take a file system path from the user, assuming the file system path is like a function parameter, how we're using it. And then you get the file pointer that you can pass to the C API. And then the C API doesn't have to know anything about Unicode. It just knows that it can write to this file. That works great. If you don't have to use C APIs, std fstream, basic fstream supports file system path, so you shouldn't have to worry about this. It should just all work. Printing doesn't really work. I wish it did. It kind of works in some ways. So I showed before that assuming you have the UTF-8 flag on MSVC, you can just make a character, any sort of char-based string with emoji in it, and you can stream that to std cout, and that'll work. For whatever reason with wide strings, even on Unix platforms, on every platform it works the same. It'll print all the way up to the thumbs down emoji, and then it won't print that or anything else after that. So the thumbs down and the new line don't get printed with wcout, which I don't get because on like macOS and Linux, that's a UTF-32 string. You would think it would like just kind of work, but it doesn't. That's another reason why I say don't use wide strings. I don't think they're that great or useful. You can just shove a U8 string into a const character pointer, or rather just reinterpret it as that. I can't guarantee you this is defined behavior, but I can say it works for me. So I don't know if Ben's gonna like that line of code, but it did seem to work.
It's certainly undefined behavior, but it works.
Right. So if you have a U8 string and you want to print it, yeah, good luck. Either use the file system path, hack, use this hack, or bring in a third-party library to do like a proper conversion to a standard string.
On the previous slide, you converted a string to a W string. Did that not do the code point conversion for you?
This is assuming that the string view only contains ASCII text.
But it turned,
It would be an invalid use to say I want, because when you're opening a file, you're saying like R plus W. If you put like an emoji in there, that would be kind of cursed. So I'm just kind of like assuming, what is worth this is only used internally and like
Yeah,
really sample
not-
where I use it.
if you assume it's ASCII, I see how that would work, but
Yeah, if this were like a true public interface, then you have the previous problem of API design is weird with this stuff, where your interface should either entirely be char-based UTF-8 or only char-based ASCII, or use one of the strong types like U8 string. So try not to mix and match. But if you start to ship stood string interfaces or stood string view interfaces that have to be ASCII, document that really well, and probably don't use char for UTF-8 anywhere else. So try to be consistent. But the type system only gets you so far here. Add some runtime checks, better docs, something. It's kind of an open question how to design interfaces with Unicode strings in mind. So one thing that I did need to make this work on Windows is set console output CP UTF-8. Couldn't tell you what this function is, but it fixes a lot of issues trying to print Unicode characters, UTF-8 characters to std out. That doesn't get you all the way there. I had some issues where I tested this out on the Windows machine that I do have, and it worked. And then I tried to run this in CI, and it gave me mangled text. And what we actually found out was going on is that the terminal that GitHub Actions was using in its Windows Server CI image was using, I believe, like a Swedish code page. Code pages or something else, but it's basically a mapping of byte sequences to actual printed characters. So it was basically like acting as if it was some country in that part of the world. It was a code page. Let's say it was Swedish. It's close enough. And it gave us this like kind of mangled byte sequence. So I think what's going on here is that your C++ program can output the exact bytes of UTF-8, but your terminal and your font renderer have to actually interpret it that way. And your code doesn't control what happens on the other end of stood out. So if your terminal doesn't interpret it correctly, it's just not going to work. So use UTF-8 everywhere is what I would say. But if you're trying to write portable code, I actually don't know how to necessarily make sure that your Unicode characters appear in the terminal of every user in every use case. So if there is a way, please let me know. But I'm not aware of one. Stood print, as far as I can tell, it's just stood format plus stood cout. It's great. I love it. I think you should use it too. But as far as I can tell, it doesn't improve on the situation. If you use stood print, I get the same garbled text output with the Swedish code page terminal on Windows. Stood print did change that. There also aren't overloads for the Unicode string classes. So the UTF-8 1632 string and string view overloads don't exist. You have to use string. You have to use a char-based or a wchar-based input for those functions for them to work. So stood print, it's great. It doesn't make Unicode any easier than it was before. You can do this. I don't really know what to say about it. It seems to be standard. Not all characters, all Unicode characters are valid Unicode, are valid identifiers. Emoji are an example, they're not. I think Swift lets you use it. This is a judgment call. If you think that these identifiers with non-ASCII characters are the best choice for your project and your team, then go for it. But if you're unsure, or if you're working in code that's kind of broad, like generically used, like any major open source project, you need to assume that the user base is going to be fairly worldwide. And the lingua franca of coding is English, which maybe upsets the French that we use that word that way. So maybe just take the ASCII. But it works if you really want it. So what have we learned? Literals are really good. When people complain about Unicode support in C++, they're not talking about the literal support. They probably don't know all the weird stuff that we just talked about. There's really, really good support for making literal strings in your code in every way that I think you could ever want to make them. I think the committee has done a fabulous job covering every use case, even with weird encodings, people who like octal. Don't talk to me if you like octal. I actually don't want to know anymore. So that's great. But that's kind of where we start to go a bit downhill. Manipulating UTF strings, very risky. Like technically the interfaces exist. You can like push bytes into a UTF-8 string, but you have to encode them yourselves. You could take another string literal and then like byte by byte stream that, or Yeah, there's not great functionality there. Also, converting between it is lacking. There are hacks that I showed. I think that's very fun, and maybe you have a use for that. But that functionality doesn't exist in the standard in the way that we want it to. Wide strings kind of suck. Don't use them. UTF-8 is really good. Definitely use that everywhere. If after all this you're like still a little dizzy about all these encodings, just use UTF-8. All of your ASCII stuff naturally is UTF-8, and all of your tools are going to support it. Your editor compiler should work just fine. You good?
Yep. Yeah.
And we need a Unicode aware string container. I wanted to mention it earlier. Unicode has their own library called ICU, which provides a C++ interface and I think a C interface in Java too. And that is, I think, the canonical library to use. It is by the Unicode consortium. So if you're doing really sophisticated stuff, if you start dealing with like normalization forms and all sorts of other more sophisticated things, I think that's probably the first place to look. I'm not an expert in it, but that's certainly where I would go first.
Using boost.txt. The
No, I haven't
relatively
actually
new
looked at
library
that.
is by Zach Lane,
Is it? Oh, it's like a newer library.
couple of years old.
Okay, boost.txt.
Zach's done some really good work on it.
So there's a lot that it has, but there's a lot more that it doesn't have. So use the parts that work, but understand where those limitations are. And then if you need to go past those limitations, then make sure you do so responsibly. Thank you.
Is there like a story or an infamous post that led you to discover that you could just completely abuse stood file systems?
I'm just like, not to brag, I just discovered it. Like this language is so big. I've been coming to Meetup for years. I've watched a ton of talks. There's a lot of stuff that feels like it's hard to find new grounds. That'd be a good lightning talk. So no one take that idea. I'm at CPCon dibs on the lightning talk. No, I'm trying to think how I found it. I think it was because I was working a lot on a library that had file system path in the interface a lot, and we needed to print the name of the path to the console. And that's when we started to realize stuff like, if you have a file system path that has non-ASCII characters and you call .string, that will throw on Windows. So we were calling .string to convert the file system path into a standard string and then streaming that to cout, like normal stuff. And that would throw on Windows because we had like emoji in the file path, which is totally valid for the file system and totally valid for file system path. And then we're like, okay, well, there's like a UA string function. And then after that, I started to I think the gears started to turn. I was like, oh, you can construct it from anything and you can convert it into anything. This is now a re-encoder.
Just put an interface around it and hide the file system. So
I should make a joke Unicode conversion library, which is just like wrappers. I was like, don't look at the implementation. First context.
Implemented a Unicode converter in 10 lines of code.
Really good, Plus on Hacker News or something. I love that.
4 minutes of explaining Unicode and the complexities of it and how it's really difficult, and then just one line at the end where you're like, look.
Absolutely.
Mic drop.
I wanted to be added to this slide. Not only can you name variable names after Unicode, you can also do it class names. So you can end up with some very dumb lines.
I think that's explicitly disallowed now.
Oh,
I want to say 23 killed that. Okay. Yeah, that's what I read, is that it used to be kind of allowed. I think it might have been implicitly allowed, just kind of by a lack of explicitly disallowing it.
I'm on ARM GCC trunk for 23 right now, but.
And you're compiling in 23 mode?
I did have no
Unicode, not
issues.
emoji.
Yeah.
Pardon?
He said Unicode, not emoji.
Oh, I thought you were using a siren emoji. Is that what I saw?
I'm using a fox and a dancing man.
Huh, okay.
I think JF has.
Emoji is Unicode, right?
Do you have references for where you got all this information?
I do, not on my slides, in my notes I do. So I've got a lot of great talks. If you want to learn more about Unicode itself, my talk is avoiding what they talked about to not overlap too much. So there's a lot of great talks about Unicode itself, which include more information on how the encoding works, dealing with error cases, some other Unicode aware string classes that people have been promoting at conferences. And I can share those. I'll probably share those in the Discord. I think that'd be a good place to do that.
Pedantic makes it not work in GCC.
Only
Yeah.
23 mode or?
Oh, let's go back.
Sorry, I have pedantic questions. Pedantic component.
One of the 9 identifiers.
Yes, okay. One of them was in the talk. File. Yeah,
File.
I'd like stop myself from mentioning that. I hope someone noticed. Yeah. Stood all caps files. File pointer.
Reset. Is it called reset?
That's not the ones that I have in mind. Oh, the iOS one, it's like stood, iOS base, and
Yes,
NIT.
init, that's it.
So that's 2 of them. So stood file and stood iOS base and NIT. There's 7 more identifiers with capital letters in them. And y'all can't leave until you name them. I'll lock the doors.
Yeah, how many of them aren't CAPI ones?
Yeah.
I didn't.
They're all standard C++. Like they're not C
Inherited
routers.
from CA.
They're not inherited from C.
Files inherited.
They're originally added in. I'll give you a hint. All 7 relate to each other.
What are we talking about?
I guess standard library identifiers that include a capital letter.
Is underscore bool capital?
Someone had in mind underscore what? Bool?
That's
True?
C, not C++, I think.
The true and
Yeah, it says
false.
an underscore.
Is it something to do with max and min?
No. I also like there's not like char max, like those are inherited from C, which I guess they count in a sense, but those are macros, aren't they? Macros are not identifiers.
Those, char bit.
The suffixes to like
Those are not standard library. Those are not identifiers. Those are like syntactic constructs of language.
so those integer limits.
No, those are, I think those are macros, like int max, like int32 max, float max.
I think they are capitalized though
They are all caps, yeah,
but in the,
inherited from C.
but going through numerical limits though, not the macro form from C.
Yeah, the numeric limits max, that's all lowercase underscore delimited, like the normal style of the standard library.
The stuff in the numbers header?
No,
No, that's all lowercase.
it was added in 20. I'll narrow it down. I will hold you hostage. I'll give you that. Something that Howard Hinton added. You know him?
Time.
Date and. Oh, it's the names of them. It's Monday, Tuesday, Wednesday, Thursday, Friday.
Today's the week. Monday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday are the other 7. So, thank you.
The months are?